Let's take a look at the sampling distribution of the ratio of sample variances. Let S1 squared be the sample variance of N1 independent observations from a population that has a variance of sigma 1 squared. This is our usual sample variance with N1 minus 1 in the denominator. Let S2 squared be the sample variance of N2 independent observations from a population that has a variance of sigma 2 squared. And suppose that these samples are independent of one another. The ratio of sample variances estimates the ratio of population variances. The expectation of each sample variance is its population variance. But ratios of statistics can be a little tricky to deal with at times, and the expectation of a ratio is not equal to the ratio of the expectations. Here, the expectation of the ratio of sample variances is actually greater than the ratio of population variances. The ratio of sample variances is therefore a biased estimator of the ratio of population variances. It's a little too big on average. The size of the bias depends on a few factors, including the sample size of the sample variance in the denominator. I'm not going to get into the details of that here. In most cases, the bias won't be very large, especially for large sample sizes. So the expectation of the ratio of sample variances will be pretty close to the ratio of population variances. If we are sampling from normally distributed populations, then S1 squared over sigma 1 squared divided by S2 squared over sigma 2 squared has an F distribution with N1 minus 1 and N2 minus 1 degrees of freedom. And we use this property to construct the appropriate confidence interval and hypothesis testing methods for the ratio of population variances. I'm going to re-express this quantity as the ratio of sample variances times this ratio of population variances. And in this video, to simplify things a little bit, I'm going to look at the case where we are sampling from distributions that have the same population variance. So the population variances will cancel out, and we'll just be looking at the ratio of sample variances. If the population variances are different, then the situation will be very similar. The values of the ratio of sample variances would simply be multiplied by the appropriate constant. Now let's sample from a few different distributions, and look at the sampling distribution of the ratio of sample variances in each case. We'll start with sampling from normal distributions. In this first case, we'll sample from two normal distributions that have the same variance. And to make this video of manageable length, I'm only going to look at equal sample size situations. Here, N1 and N2 are both equal to 5. In this scenario, the ratio of sample variances S1 squared over S2 squared has an F distribution with 4 degrees of freedom in the numerator and 4 degrees of freedom in the denominator. That's what this red curve represents. We can see that for these sample sizes, the distribution of the ratio of sample variances has some pretty strong right skewness. That skewness is going to decrease as the sample sizes increase. To verify that the ratio of sample variances has this distribution, I'm going to simulate 100,000 values of S1 squared and 100,000 values of S2 squared in this scenario, and plot a histogram of the values of their ratio. And that's what this gray histogram represents, 100,000 simulated values of S1 squared over S2 squared. And we can see that it fits the red curve quite well. I'm truncating the plot over here at 6, but this ratio can take on any non-negative value, and about 5.5% of the values are greater than 6 for these sample sizes. But when we increase the sample sizes, it will be much less. Now let's increase the sample size to 20 and see what happens with the distribution. The scaling on the y-axis is going to be changing from plot to plot. And rather than change the plotted values on the y-axis, I'm simply going to leave the y-axis off the plot. All of the curves I'll be plotting are continuous probability distributions, and they have an area of 1. For this plot, the sample sizes are both 20. The red curve is the F distribution with 19 degrees of freedom in the numerator and 19 in the denominator. This is the true theoretical distribution of the ratio of sample variances in this scenario. And we can see that the histogram of 100,000 simulated values of the ratio of sample variances follows the red curve quite closely. If we increase the sample sizes to 100, we have a similar story, just with less variability in the distribution. It's more tightly grouped about 1, which is the true ratio of population variances, since they're equal in the scenarios we're looking at. Now let's sample from some non-normal distributions and see what happens. Here we'll be sampling from this distribution in blue, which is a uniform distribution. This green curve represents a normal distribution with the same mean and variance. The uniform distribution has a flatter peak and lighter tails than the normal distribution. Because of this, we say that it has lower kurtosis than the normal distribution. An implication of this is that the sampling distribution of the sample variance has lower variability than if we were sampling from a normally distributed population with the same population variance. Let's see what consequences that has for the ratio of sample variances. Here the samples are drawn from uniform distributions with the same variance and sample sizes of 5. The gray histogram represents 100,000 simulated values of the ratio of sample variances, which is approximately the sampling distribution of the ratio of sample variances in this scenario. The red curve represents the theoretical sampling distribution of the ratio of sample variances if the populations were normal. It's an F distribution with the appropriate degrees of freedom. We get a bit of a clearer picture of the situation if we increase the sample sizes a little, so let's look at sample sizes of 20. We can see here that the gray histogram has lower variability than the red curve. The sampling distribution of the ratio of sample variances is less variable than when we are sampling from normally distributed populations. And if we increase the sample sizes to 100, we see a very similar situation, just more tightly grouped about 1, the true ratio of population variances. Now let's look at a distribution that has heavier tails than the normal distribution. Here we'll sample from this distribution in blue, which is the T distribution with 5 degrees of freedom. I'm superimposing a normal curve in green, and this normal distribution has the exact same variance as the blue curve, but the blue curve has a sharper peak and heavier tails than this normal distribution. It's a little hard to see from this plot that the blue curve has heavier tails, meaning more area out in the tails, but it does. Because of the sharper peak and heavier tails, we say that the distribution in blue has greater kurtosis than the normal distribution. This will result in more extreme values of the sample variance S squared. The sampling distribution of the sample variance has greater variability when we sample from the blue distribution than when we sample from a normal distribution with the same population variance. And this has implications for the ratio of sample variances. Here we are sampling from the heavier tailed distribution we just looked at with sample sizes of 5. And it might look like the red curve fits reasonably well, but there are some systematic differences. The differences will be easier to see if we increase the sample sizes a little bit. Here are sample sizes of 20. And we can see that, compared to the red curve, the gray histogram has a greater frequency of smaller values of the ratio of sample variances and a greater frequency of larger values, and values near the middle are less common. In other words, the ratio of sample variances has greater variability than if we were sampling from normally distributed populations. And that effect is perhaps even a little more clear when the sample sizes are 100. The gray histogram of simulated values is showing greater variability than the red curve. And that effect would be even more extreme if we were sampling from distributions with even greater kurtosis. Let's take a quick look at a summary of the important points here. When sampling from normally distributed populations, the quantity S1 squared over sigma 1 squared over S2 squared over sigma 2 squared has an F distribution with N1 minus 1 and N2 minus 1 degrees of freedom. And when the population variances are equal, the ratio of sample variances has this distribution. When sampling from non-normal populations, the variance of the sampling distribution of this quantity can be much less or much greater than when we are sampling from normally distributed populations. An implication of this is that inference procedures for the ratio of population variances that are based on the assumption of normally distributed populations can work very poorly if the normality assumption is violated. In another video, I'll take a closer look at the effect of a violation of the normality assumption on these inference procedures. But let's save that for another time.